Hello, we're still working with line integrals. We're still in 16.2, but now we want to look at what happens if we're looking at a line integral that's just with respect to x or y. So if we are asked to calculate a line integral with respect to just x or y, and not ds, but like dx and dy, then we need to figure out like a similar definition. So if we replace delta s with delta x or delta y, then we get these interesting looking integrals. And the reason I say they're interesting is because for somebody who doesn't know, it looks like I'm asking you to integrate a multivariate function with respect to only one of the variables. And I'm not. I'm not, because if we did that, then we wouldn't get a numerical value. We would get, like for example, with the dx, we would end up having y's still left, okay? This is a line integral, and the thing that's there to let you know that it is a line integral, not a regular integral, is that the fact that it's over a curve C. And so what that means is that C is going to have parametric equations. We're going to be able to come up with some vector function R of t, right? R of t will be the vector with components x of t, y of t, and if we go any further, it'll be z of t, okay? And then from that, what we can get is, so we can find that r prime of t, I'll just write this as, let's see, r prime of t dt is equal to x of t dt, sorry, x prime of t dt, y prime of t dt, and z prime of t dt. And so what that can tell us right there is that when we're trying to figure out what to replace dx with, well, we go to the r prime of t dt and we focus on the x component of r prime of t dt, which is x prime of t dt. Similarly for dy, if I'm trying to replace dy, then I need to go to the y component of my vector function and pull out a y prime of t dt. It may be simpler for some of you to look at the parametric equations in this way. So it's the exact same thing as what I've written, except it's in parametric form. We have x is x of t, y is y of t. We can take little d of both sides and get dx equals x prime of t dt, and dy equals y prime of t dt. All that I'm providing you with is two different ways to represent the exact same information, okay? Now, a weird thing that ends up happening in line integrals is this notation right here. You're going to see notation like this a lot, where it's integral over c, and then it appears to be a sum in the integral, and there are two different differentials. So it's f of xy dx plus g of xy dy. Now, it's almost like there's an integral missing there, but it's not. The way we have to translate that is to replace all x's and y's with their x component and y component from r of t, and then we need to replace dx and dy with x prime of t dt and y prime of t dt. What ends up happening is we get this next representation, which is exactly what we think it is. It is a single integral with respect to one variable, t, and that's it. We just have to replace all the parts, right? We have to get our integral of a multivariate function to be parametrized down to a single variable function. That way, we only need one integral in order to integrate. So first, here's your steps. You're going to determine if you have been given a parametrization R of t of your curve C, or if you need to come up with one. Before I go into step 2, I want you to look at this table. We have some common parametrizations that you could come across. Like if you're given an ellipse, I've got a parametric equation depending on whether you need a counterclockwise rotation or a clockwise rotation. Same with a circle. We have both of the different types of rotations and the parametrizations. And then explicit functions of x or y. We've got those there. And then how to create a line segment, which is something we learned in chapter 12, I believe. This table of common parametrizations is on your formula sheet, so definitely get to know it well, know how to use it. You won't always need it, but if you have not been given an RFT, you've just been given a description of your arc, your C, then you may have to come up with one, okay? So then after you've come up with or been given your R of t, you need to find R prime of t and the magnitude of R prime of t. And then you need to evaluate your scalar function at R of t, and then you just pop everything into your line integral and integrate. And then you're going to evaluate from whatever the bounds of t are. So a few points. This is kind of a loaded page here. There are a few points, and some of them we've already made. So in the first one, it's similar to the example that we already did, where our curve C was made up of two curves, and we had to integrate over each curve separately and then add them together. That's all that number one is saying. So if your curve C is broken up into 18 parts, then you're going to have 18 line integrals that you have to parameterize and set up and then evaluate. We're not going to have any with 18, maybe 3 or 4 is the most, okay? One physical interpretation of a line integral is to integrate the linear density function of a wire over the curve that represents the wire, and then that would result in giving us the mass of the wire. And so if we knew the density rho of xy of a linear function of a thin wire, then we could calculate the mass just looking at the line integral over C of the density times ds. And then we could find the center of mass, x bar and y bar, by calculating moments and dividing by the mass. Okay. In general, this is step 3, or note 3, the value of a line integral depends not just on the endpoints, but also on the path. Now, this is in general. We will have some special cases that come up later on, but it is important to know that if we do not have a special case, then the value of our line integral will depend on the path and on the endpoints. And we'll learn later when we don't have to worry about the path. In general, the direction traveled is also important. If the parametrization gives an orientation for the curve C, then the positive direction corresponds with increasing values of the parameter t. Note 5, changing the direction of the integration will change the sign of a line integral if we integrate with respect to just x or y. So changing the direction of the integration will change the sign of the line integral if we integrate with respect to just x or y. But if we integrate with respect to the arc length ds, then the value of the line integral does not change when we reverse the orientation of the curve. So what I'm saying here is, if we're going in a different direction along C, so negative C, we can interpret that as giving us a negative value on the regular line integral over C if we're dealing with dx, or if we're dealing with dy. Okay, but if we have ds, remember, is going to be the square root of the sum of squares, x prime of t and y prime of t, and so those are always going to be positive. And so that means that if we integrate if we go in a different direction along the curve C, it's not going to change the value in front of the line integral of going over in another direction along C. So the reason it changes up here is because dx is x prime of t, that's a terrible t, of t dt. And so what that means is that x prime has a sign with it. We're not squaring it and adding it to a y prime squared and then taking a square root. So we're going to get a sign. Okay, and the same for dy. We're going to get a sign there. Let me get my... So this guy right here, this is y prime of t dt, and it also has a sign. Okay. All right, one way to picture what is being measured, I already talked about this in the very beginning in the last video, is that what we are evaluating, what we're integrating, is a surface, but it is a surface only along a curve, not over the entire, like all the xy values underneath the surface, only the XY values that are on the curve. And so these pictures, especially this one, are meant to help you to see that. So this is the surface fixed over only the X and Y values on the curve C. Okay. All right. Done with that page. Now we can move on to some examples where we've got the dx's and the dy's in there, and we've got to, figure out how to handle those. All right, so in this particular one, we're going to evaluate the line integral over c of x squared dx plus y squared dy, where c consists of the subarc of x squared plus y squared equals 4 in the first quadrant going from 2, 0 to 0, 2, and the line segment going from 0, 2 to negative 1, 1. So it looks like we have a C1 and a C2. C1 is the subarc and C2 is a line segment. So let's draw this. So we have a nice clear picture of what's going on. All right, the subarc, the x squared plus y squared equals 4 is a circle with radius 2. So it does go through 2, 0 and 0, 2 in an arc-like fashion. So that's C1. And we're going from 2, 0 to 0, 2. Then we have a line segment that starts at 0, 2 and goes to negative 1, 1. And then stops there. That will be C2. Okay? So let's get our colors out. C1 is the x squared plus y squared is equal to 4. And so the best way to parameterize a circle is to let x equal the radius times cosine. So our radius is 2, so we get 2 cosine of t, and y is equal to 2 sine of t. If we have those, then we can say, all right, our r of t is equal to, well, maybe actually I won't do it this way. I won't do it with the vectors. I'm going to do it with just finding the dx's. So if x is 2 cosine of t, then dx is equal to negative 2 sine of t dt. And dy, if y is 2 sine of t, then dy is equal to 2 cosine of t dt. So those will be my replacements for the x squared, the dx, the y squared, and the dy. But now I also need to know, what is t doing? Well, I can see that we're in the first quadrant only, from 0 to pi halves, so that's what t is doing. T goes from 0 to pi halves. That will take care of my C1. For C2, I have a line segment, and it looks like I could come up with the function that models that line segment. And, well, it's y equals, I know that much. And the slope on that is a positive 1. So I have a 1x, and the y-intercept y value is 2. So just 2. Okay, for this, I could let, since I have an explicit function, I'm going to let x equal t and y equal t plus 2. I'm going to calculate my dx. dx is 1 dt. I'm going to calculate my dy. dy is also 1 dt. Okay? Now, it looks like, look at our arrow. Go back to the drawing of C2. The arrow starts at 0 and goes to negative 1. That's kind of weird. We're used to setting up, like, let's see, the orientation of the curve has t going from 0 to negative 1. But we might set up an integral with -1 is less than or equal to t is less than or equal to 0, just out of habit, right? We might be like, oh, well, the t values are from -1 to 0, but really they're from 0 to -1, which is like super weird. So let's see how we're going to handle that, okay? All right, when I write this out, I have got my integral over c of x squared dx plus y squared dy, okay? I am going to look at this. It needs to be broken up into two pieces. I have my integral over c1 of x squared dx plus y squared dy, and then I have plus my integral over c2 of x squared dx plus y squared dy, okay? Now, when I set this up, the first one is not so bad. Let me go ahead and write that one out. The first one, t is going from 0 to pi halves, and that is also the direction along my curve, right? So I start at 0, I go to pi halves, the arrows are pointing in that direction, so everything is good. My bounds are in the same direction as the curve travels. I need to replace the x squared. I go to c1, x is 2 cosine t, so I square that and I get 4 cosine squared of t. dx is -2 sine of t dt. And then I have plus y squared. Well, y is 2 sine of t, so that'll give me plus 4 sine squared of t times dy, which is 2 cosine of t dt. So that is my first integral over c1. c2, now, if when I'm setting up integrals, I automatically say, okay, I'll go from -1 to 0. We'll go ahead and write it that way. And now the x squared, I have to go to my c2 parametrization. X is t, so I have t squared. dx is 1 dt. Plus y squared, well, y is t plus 2, so I have a t plus 2 all squared, and my dy is 1 dt. Okay, I'm going to put some parentheses around each of these so that I know that they belong to their respective integrals. All right, the first one I want to rewrite just a little bit more nicely, and I'm going to factor out a dt when I do that. The integral from 0 to pi halves of -8 cosine squared of t sine of t plus 8 sine squared of t cosine of t, and then close that and I have my dt. Now, on the other one where I have the integral from -1 to 0, that is in the opposite direction of the orientation of my curve, okay? And this integral had dx's and dy's. It did not have ds. And so what ends up happening there is I say minus the integral from 0 to -1. So now I have my bounds going in the same direction as my curve travels. I know that that's really weird, but it is something you need to pay attention to, okay? So that's why we're doing it in a video and an example. All right, so I've switched my order of integration, made things negative in order for me to be going in the correct direction. Now, inside of my integral, I have a t squared, and then that t plus 2 all squared becomes t squared plus 4t plus 4, and then I have my dt on the outside. Okay, it looks like we are ready to integrate, other than the fact that t squared plus t squared is just 2t squared. Okay, now the purple one, 0 to pi halves, I have this -8 cosine squared times sine. I need a u sub. So I'm going to do, and the other one I also need a u sub, so I'm going to do 2 u subs. One will be u, one will be w, okay? The first one, u is going to be the thing getting squared, so the cosine of t. du is going to be minus sine of t dt. So now I'm taking care of the minus, I'm taking care of the sine and the dt, but the 8 has not been taken care of. So if I multiply my du and my minus sine of t dt by 8, I get that 8 du is equal to negative 8 sine of t dt. All right, so I have a perfect replacement right here. That means that my integral is actually the integral of 8u squared, 8u squared du, which gives me 8/3 u cubed. All right, and I'll use that in a moment. The other side, I'm going to use w is equal to so sine is getting squared, so w will be sine of t. dw will be cosine of t dt. I need an 8 in there, so 8 dw is 8 cosine of t dt. So it looks like I'm integrating 8u squared du again. Okay, so this is, sorry, not u, that'll be w. 8w squared dw, which gives me 8/3 w cubed again. Okay, so let's put this all together. All right, in my purple, I have 8/3 u, which is cosine, cubed of t from 0 to pi halves, plus I have 8/3 w, which is sine, cubed of t. You know what? I can just go ahead and do those all at the same time. Instead of doing two separate evaluations, I will do one. These both go from 0 to pi halves, so there's no sense handling them separately. And then I have minus, right, for my next one. When I integrate 2t squared, I get 2/3 t cubed. The 4t integrated will be plus 2t squared, and the 4 integrated will be plus 4t, and we're going to go from 0 to minus 1. Okay, I think we're ready to plug in. All right, evaluating cosine at pi halves gives me 0. So I get 0, and then plus 8/3 sine cubed of t. Well, sine of pi halves is going to be 1. Cubing that, it's still going to be 1. So I just have 8/3 times 1. Minus, and then I get 8/3. Cosine of 0 is 1. Cubing it just gives me 1. And then plus 8/3. Sine of 0 is 0. So that's going to go away. Okay, that takes care of the evaluation in purple. Minus, all right, 2/3 times negative 1 cubed. The negative 1 cubed will be negative, so I'll get negative 2/3. Plus 2 times the negative 1 squared is just plus 2. Plus 4 times negative 1, that'll be minus 4. And then the contribution from 0 is just 0. All right. Finally, what we get is 8/3 minus 8/3 minus, and then inside here I have a negative 2/3, a 2, and a minus 4. So that becomes a negative 2/3 and then a minus 2. And when we deal with that, hold on one second, what's going on here? Let me pause one moment. Okay, sorry about that. So I need to make a correction because, so the curve C didn't change. So this is all about my C2, okay? So with C2, I still have my curve C2. We would still look at the bounds going from 0 to negative 1. What is being said, let's see, when we go from negative 1 to 0, is that, let's see, how do I phrase this? Um, Trying to think of the best way to phrase this without it uh, being weird. So let's see. I'm not sure if I have a good way to phrase this because, okay, maybe I should just talk through what went on. So right here, when I had the integral from -1 to 0, and then I switched it from 0 to -1, and I put the negative sign on the outside, I didn't, that negative should not have gone there because we have this, let me just pull it up right here. We have this statement right here that says that if we were to switch those bounds around, we are going to get the negative of what we would have gotten. Okay. Um, and I don't know a good way to say that other than right here, instead of this being a negative, this should have been still a positive. Okay, so we're going to switch the bounds around, but by switching them around, we're like, we don't pull out a negative at the same time because all we're doing then is balancing things out. So when I switched that sign to a negative, I was doing something that we learned in Calculus 1, which is if you want to switch the bounds, you just need to put a negative out in front when you switch those bounds, and then everything stays like the same. You don't end up actually changing your sign. And so I was kind of stuck in a Calculus 1 world of, oh, I switched my bounds, I should put a negative out in front. That's actually not the point right here. The point is that, well, maybe it would be even easier if I just don't even switch right now. I leave it as -1 to 0, and then we make a comment about it at the end. I think maybe that's the best thing to do. So instead of having these minus signs, okay, I'm going to keep it positive. I'm going to keep it from -1 to 0. I'm going to keep this positive, and then I'm going to handle everything here in just a moment. Okay, I think that's the best way to deal with this. Okay, so the contribution that we get, maybe I should rewrite this then too. Hold on, sorry. Okay, evaluating this at 0, so now I'm back to the -1 to 0 thing. So evaluating at 0, I get no contribution. Minus the evaluation at -1 gives me -1 cubed is negative, so I get a -2/3. -1 squared is positive, so I have +2. 4 times -1 is -4. Okay, so the contribution from the first integral gives me 8/3 minus 8/3, plus the contribution from the right integral, or the second integral, is going to be, looks like we get 8/3 from that. Okay, but this, so on the right, in the purple, I've got the 8/3 minus 8/3, which is just 0. And then this one needs to be opposite in sign because we need a forward direction on the curve. So what we're saying here is that the integral from 0 to -1, right, of the t squared plus the t plus 2 all squared dt is going to equal -8/3. Not positive 8/3, but a negative of what we got when we had the bounds written in the correct order. And since we got no contribution from purple, we only got contribution from the second, the C2, our overall answer is going to be this -8/3. plus the 0, which just means -8/3. I'm really sorry if that's confusing. If you are having questions about this idea as you go through your homework, please reach out, because I do know that it can be confusing. And and really examine your sub arcs like C1, C2, and see if by having normal bounds, like going in a numerical order, would make you travel along the curve in the wrong direction. And if it does make you travel along the curve in the wrong direction, then you're going to have to make it negative when you get your final answer. Okay? All right. Another example, example 5, we're going to evaluate the line integral over C of y dx plus z dy plus x dz, where C consists of the line segment C1 from 200 to 345, followed by the vertical line segment C2 from 345 to 340. So let's, that sounds horrible to draw. Well, I guess we got to do it anyway. So let's get an actual pen here. I'm drawing my X, Y, Z octant slightly off center for a reason, just so it's easier to see my line segments that I have to draw here. Okay. So for the line segment from 200, that's right here, to 345. So 345, go 1, 2, 3, and then go out 1, 2, 3, 4. Okay, so that's where it would be on the XY plane. Now we go up 1, 2, 3, 4, 5 units. Okay, that's 345. So this was 200 to 345. This gives me C1. Okay. C2 is starting from 345 and then going to 340. So 340, well, that's actually just going straight down back to the XY plane. Okay. All right, so we have our 2. This is C2. I'm going to 340. All right, let's play with C1 first. C1, oops, wrong color. C1 is the line segment that is connected by the 2 points 200 going to 345. Well, to create a line segment, we need a parallel vector, V. So V can equal the 3 minus 2, 4 minus 0, 5 minus 0. So I'm just creating a vector between those 2 points. This simplifies to be 1, 4, 5. And then we need an R naught. R naught is always the first point that's listed, 2, 0, 0. And then we can come up with a vector function of the line segment. R of t will be, remember, R naught plus TV. So this gives me 2, 0, 0 plus t times my v, 1, 4, 5. And this simplifies to be 2 plus t, 4t, and 5t. And with any line segment, the t values go from 0 to 1. Okay, so that's my R of t for C1. And now I need R prime of t dt, which will equal, it looks like 1, 4, I should write this as 1 dt, 4 dt, and 5 dt. So that gives me my parts that I need. And then I need to do C2. Got to get that taken care of. So C2 is very similar. We have a point 345 going to the point 340. Again, I need to create a parallel vector, V. So I'll start at the later point, subtract the earlier point. 3 minus 3, 4 minus 4, and 0 minus 5 gives me a parallel vector that has components 0, 0, negative 5. R naught is the first point given. So it's the 3, 4, 5. And then remember r of t is r naught plus tv. So I put everything in. We have our 3, 4, 5 plus t times 0, 0, negative 5. And this all simplifies to be 3, 4, and 5 minus 5t. Then I need my r prime of t dt. And that is going to be, looks like 0, 0, negative 5 dt. Okay, so we have the two parametrizations. It looks like I used the wrong color to draw to do my C2. Let me change that color then to purple. Okay, so everything just kind of lines up color-wise. All right, so we have this integral, line integral of y dx plus z dy plus x dz, and we've got to evaluate that over these two curves. So the integral over c of y dx plus z dy plus x dz will have to be two line integrals, 1 over c1 of y dx plus z dy plus x dz, plus another line integral, but over c2. I need to stay consistent with my colors. All right, so the first one, line integral over c1, was in blue. So it's going to be the y dx plus z dy plus x dz. And then plus the line integral over c2 of y dx plus z dy plus x dz. Okay, so now I have to go to c1 and pull out all my parts and put them in. So this is equal to the integral. Let's see, our bounds are 0 to 1. And y, it looks like, is 2 plus t. That's the y component of r of t is 4t. So I get 4t. The dx component, that comes the first component in r prime of t dt, that's going to be 1 dt. Plus z from r of t, that's 5t, times dy, which is 4 dt. Plus x, which is 2 plus t, times dz, which is 5 dt. Okay, that's the line integral over c1 plus the line integral over c2. Oh, I forgot to put bounds on this. It's a line segment, so it's still, t goes from 0 to 1. So we'll do 0 to 1 down here. Now I need to replace all the things from our c2 parametrization, where y is 4, dx is 0 dt. So we're going to get nothing from that. Plus z, which is 5 minus 5t, times dy, which is again 0 dt. Plus x, which is 3, times dz, which is negative 5 dt. So that'll be our contribution. All right, let's rewrite this. The first one, I have 0 to 1 of 4t plus 20t plus 10 plus 5t, and then dt, plus the integral from 0 to 1 of negative 15 dt. Okay. You know, it looks like we have the same bounds, and we have a sum of integrals. It means we could take the integral of a sum, so I can combine these into one. I'm going to do that. It's the integral from 0 to 1. I have a 4t, a 20t, and a 5t. That means I have a 29t. I have a plus 10, and from the other integral, I have a minus 15, so it's minus 5 dt. All right, this is going to give me 29 over 2t squared minus 5t from 0 to 1, which gives me 29 over 2 minus 5 and then minus 0. 29 halves minus 5. I can rewrite the 5 as 10 over 2, and this gives me 19 over 2 for a final answer there. Okay, so that one was kind of intense. We had 3 variables. We were in R3 and had to create line segments in there and get all the parameterizations and then put them together in the integrals. So it's a bit of work. Let's look at another one from this section, and then that will be our last one, and I'll do a third video. Okay, here we're asked to evaluate the line integral of z dx plus xy dy plus x dz. X is, our curve C is defined by x is sine of t, y is cosine of t, z is tangent of t, and they give us bounds for t. It's going from minus pi fourths to pi fourths. So I'm just going to go underneath my C definition and write my dx, dy, dz. So if x is sine of t, dx is cosine of t, dt. If y is cosine of t, then dy is minus sine of t, dt. And if z is tangent of t, then dz is secant squared of t, dt. Okay, then let's see, I think I have all my parts. I can go ahead and put stuff in. So we're looking at the line integral over C of z dx plus xy dy plus x dz. This is the integral from minus pi fourths to pi fourths, according to what they gave us. Z is tangent of t. Dx is cosine of t dt. Plus xy will give me sine of t, cosine of t. Dy will give me a minus sine of t dt. X dz will give me sine of t and then times secant squared of t dt. Now, I need to do some serious cleaning up by rewriting stuff in terms of sines and cosines and seeing how, or just anything, seeing how I can clean this up a bit. So I'm looking at the first part, minus pi fourths to pi fourths. That tangent of t is sine over cosine. Sine over cosine times cosine is just sine. I'm going to take my time writing this out though so that it's not like voodoo. So I have sine of t over cosine of t times cosine of t in my first term. The other one, I can't really do much with that. It's just minus sine squared of t cosine of t. That's going to use a u substitution. Plus sine times secant squared. Well, secant squared is 1 over cosine squared. I'm going to write that slightly different. I'm going to write this as sine times 1 over cosine of t, but I actually have 1 over cosine squared. I'm going to put the other cosine under the sine. So I still have cosine squared. I just kind of broke it up a little bit for convenience sake. All right, so this simplifies. Minus pi fourths to pi fourths. The first term, the cosines divide out. I am left with sine of t. The second one, there's no hope for it. It's just sine squared of t, cosine of t. The third one is tangent times secant, or otherwise written as secant tangent. And I rewrote it that way because the antiderivative of that is just secant, so I don't have to do any funky u subs or anything. That makes that easier. So I just have one u sub right here. I'm going to go off to the side and deal with it. U, my u sub, u is equal to the thing being squared, so that'll be the sine of t. Du is going to be cosine of t dt. I have a minus sign there, so I'll replace it. Minus du will be minus cosine of t dt. So I have a perfect replacement. minus sign and all. So this is the integral of minus u squared du gives me a negative 1/3 u cubed. Okay, let's go ahead and put that in. Yeah, okay. So when I take care of this, I'm going to get the antiderivative of sine is minus cosine of t. The antiderivative of minus sine squared cosine of t is minus 1/3 sine cubed of t. The antiderivative of secant tangent is secant of t. And we're evaluating from minus pi fourths to pi fourths. Okay. Cosine of pi fourths is going to be a minus square root of 2 over 2. The minus comes from the sign that's there. Minus 1/3. The sine of pi fourths is also root 2 over 2, but I'm going to have to cube that. Plus, secant is 1 over cosine. So what I'm getting here is 1 over the square root of 2 over 2. Okay. Minus the evaluation minus pi fourths. Okay, negative. Now cosine of minus pi fourths, we're in the fourth quadrant. It's still going to be root 2 over 2. Okay. Minus 1/3. Sine of minus pi fourths is negative square root 2 over 2. And then we're going to cube that. Plus 1 over cosine, because I'm dealing with secant here, so I'm going to plug it in as 1 over cosine. So cosine of minus pi fourths is still positive, root 2 over 2. Okay. If I distribute my negative sign and rewrite all of this, what I end up with is negative root 2 over 2. I get a plus root 2 over 2. I have a minus 1/3. Oh, I'm going to go ahead and leave this still uncubed. I'll deal with it in a minute. And then I get a plus. Oh no, maybe I will go ahead and cube this. If I cube a root 2 over 2, I get 2 root 2 over 8. Okay. And then when I've got the one that's inside, when I cube a negative root 2 over 2, I'm going to get a negative times the negative that's in there, that'll become positive, times the negative that's on the outside right here, that'll become negative 1/3 2 root 2 over 8. Okay. Plus the 1 over root 2 over 2 and minus 1 over root 2 over 2. So I wrote it this way so we could see what just goes away, right? These go away to 0. These go away to 0. I'm left with what's right here. Okay. So when I add these together, I've got a negative. Let's see, 2 over 8. Those are going to simplify. So this becomes a negative square root 2 over 12 minus the square root 2 over 12, which is equal to minus 2 root 2 over 12, which finally, the answer is negative square root 2 over 6. Okay. It looks like, we got a negative answer. And that's kind of interesting because we talk about a line integral giving us the value of the area on one side of a curtain, and this isn't giving us area because we got a negative answer. So that should lead you to believe that area is just one application of a line integral. A line integral also calculates abstract things and other stuff. So we can call this one an abstract thing. And basically what's going on here is on that interval for t, our surface is probably kind of dipping below the xy plane, and we're picking up negative values there. So something to ponder and think about. But that concludes the section on the line integrals where we have dx and dy and also dz. I will do one more video for 16.2 that's going to deal with the line integrals of vector fields. So be on the lookout for that. If you have any questions, please reach out.